Hi. In the last couple of classes, we have discussed about sign magnitude method and the ones complement equivalent method. The major disadvantage in the sign magnitude method was, the major important points in the sign magnitude method was we were using one extra bit for the representation for the negative number and positive number. That is, the one bit value of one represents a negative number and zero represents a positive number. And the major disadvantage in this sign magnitude method is we had two representations for zero. The same which comes with the ones complement also. We had two representations for zero. So now we will be considering about the two's complement equivalent. So the topic for the day will be the two's complement. Two's complement. So every one of us will be aware of the concept like how to compute the two's complement equivalent of a number. Means the two's complement equivalent of a number will be equals to one's complement equivalent plus 1. So, and the major important point which we need to remember, which was same in the earlier ones complement case also, is it is used for representation of negative numbers, used for representing negative numbers only. So the two's complement equivalent for that corresponding positive numbers will stay one in the same. So this is the point which we need to remember. Okay. Next. So as in the similar case, let us take an example and let us take from minus 3, minus 2, minus 1, minus 0. This is 0, 1, 2, 3. So generally for 0, it will be 0, 0, 0 to the base of 2. For 1, it will be 0, 0, 1 to the base of 2. And 2, it will be 0, 1, 0 to the base of 2. And for 3, it will be 0, 1, 1 to the base of 2. And as we have already discussed, the 2's complement equivalent for the positive numbers will remain one in the same. Now, let's come to this finding out for a negative number. How to find out the 2's complement equivalent for number minus 3? Whatever the previous methods which we were using, we will be preferring the same method. That is, first we will be writing down its equivalent in a 3-bit format 0, 1, 1. Later, we will first find out the ones complement equivalent. We will find out the ones complement equivalent, which will be 1, 0, 0. Later, we will be adding 1 to that. So this is add 1. So this becomes 1, 0, 1. Is that okay? So the value of minus 3 will be 1, 0, 1 to the base of 2. Now let us find it out for the value minus 2. The value minus 2. So the 2 can be represented as 0, 1, 0. So the ones complement equivalent will be 1, 0, 1. And now when I'm adding 1 to that, it will become 1, 1, 0. So this will be 1, 1, 0 to the base of 2. And now let us compute it for minus 1. So the representation of 1 will be 0, 0, 1. And it is going to be 1, 1, 0. And if I add 1 to that, it is going to be 1, 1, 1. So this will be 1, 1, 1 to the base of 2. And if I'm finding out minus 0, so the 0 can be represented as 0, 0, 0. The ones complement equivalent for that will be 1, 1, 1. And if I add again 1 to that, and this is add 1. So this one will become 0, 0, 0, and this one will be 1. Okay. But here our representation is only 3 bits. So we are going to discard. Why are we discarding it? Because our representation is only 3 bits. I am discarding it. So this value is going to be 0, 0, 0 to the base of 2. So this is how we are going to compute the 2's complement equivalent for a negative number. So one thing to observe, the value of minus 0 and plus 0 are same, which was not in the previous two cases. So this brings the speciality or a special advantage to the 2's complement equivalent. Okay. So, but if you can observe in the previous example, we were able to represent with all the 3-bit combinations, means from 000 to 111. Here, only one combination is missing. If you can observe 000, 001, 010, 011. One combination of 100 is missing. So what is that missing combination? Just a moment. The missing combination is 100. The missing combination. The missing combination is 100 to the base of 2. So when I'm telling it as 100 to the base of 2, so let us consider 100 to the base of 2 is the 2's complement equivalent, which is missing combination. Is that okay? So here the MSB is going to be 1, so which represents it as a negative number. So if it is a negative number, what we need to do? We need to compute its equivalent, 2's complement equivalent. So I'm making this one like 0, 1, 1, and again I'm adding 1. So 1101, 1101, 1. So here the MSB is negative and the magnitude is minus 4. Sorry, magnitude is 4, which tells us that 100 is nothing but the representation of minus 4 to the base of 10. This is the thing which we need to understand. So, till now, we were able to represent till minus 3 only, but here in the 2's complement, I am also able to represent minus 4 to the base of 10, which will be 100 to the base of 2. So point number 1, as there is only one representation for 0, we were able to represent one extra value. Okay. So now, whenever I'm trying to represent that particular extra value, now what happens with the range? What happens with the range? That will be the valid question. So range. So for a 3-bit value, I'm able to successfully represent from minus 4 to plus 3. Is that okay? So when I'm able to represent from minus 4 to plus 3, I can write down minus 4 as minus 2 square. 2, I can write down 3 as 2 square minus 1. So here the 2, I'm going to represent it as minus 2 of 3 minus 1. 2, 2 power 3 minus 1 minus 1. So here I'm just considering n is equals to 3. So this is going to be minus 2 power n minus 1 to 2 power n minus 1 minus 1. This is the range for n-bit representation in 2's complement equivalent, which is quite different from our two above cases. So this is the range. Is that okay? So one thing which we missed, yeah, and by the way, to make the enough or required comparisons, earlier the range was from minus 2 power n minus 1 minus 1. But here one extra bit is being represented, so that's the reason why that minus 1 is being removed. Now, one thing which we missed in our course of discussion was how can I convert an 2's complement equivalent number into the normal number. So let us consider whatever the input we had. So let us consider the first example, like the 2's complement representation is 1, 1, 1, 1 to the base of 2. So here it is the 2's complement representation. So the 1 is there. So it is the MSB which states it's a negative number. So to find out the 2's complement, it will be 0, 0, 0, 0. And I'm going to add 1 which leads to 0, 0, 0, 1. So here the magnitude is 1 and it is negative. So this is minus 1 to the base of 10. So let us take one more example. If I need to find out the 2's complement equivalent of 0, 1, 1, 1 to the base of 2. So here I can consider this one like this is the MSB and MSB is 0 represents it's a positive number. So directly we can compute this one like plus 7 to the base of 10. So this is how I can convert a 2's complement equivalent number into its normal, a normal binary equivalent number. Okay. So this ends the two's complement. So the main important things, if we wanted to review in the two's complement equivalent method is the first one, we had only one representation for zero, which was quite different from the other previous two cases. The second one we have discussed the like it is only useful for representing the negative numbers. The positive numbers will stay the same. The third point is we are able to represent one extra bit or one extra value when compared with the ones complement and the sign magnitude method. So that's the reason why we can observe the corresponding change even in the range. And this is the method which we are going to prefer. Whenever if a value is being given in the two's complement equivalent form, the MSB value plays a crucial role. For the if the MSB is 1, we are going to consider it as a negative number. And if the MSB is 0, we are going to consider it as a positive number. So this ends the today's session. If you are having any doubts, please do ping me in the comments below. Thank you.